So, good afternoon, everyone. So, today I am going to discuss regarding some algebras which are mainly evolved from the graph set theory. So, as many of us is very familiar that this Paulak is the founder of this graph set, and there are several ways to define a graph set. So here we are going to take first one approximation space, which is one non-empty set, U together one equivalence relation. Then this U is partitioned into distinct equivalence classes. Then we are going to take X as a subset of U, and we are going to define two operators on X. One is lower approximation operator, another is upper approximation operator. So loosely speaking, lower approximation operator is maximum number of classes, which is highlighted by these green blocks, entirely contained within X. And what about this X upper? The minimum number of classes, which is denoted by this yellow block, contain this X. So this is loosely speaking the meaning of X upper and X lower. So this is the definition of this. The X lower is all those elements whose classes entirely within X, and X upper is all those elements whose classes having non-empty intersection with this X. So I am not coming to this boundary. Then two sets X and Y, they will be called, we are going to define one notion, roughly equal. If these two sets are going to call roughly equal, we are using this symbol if and only if X lower is same with Y lower and X upper is same with Y upper. And this this rough equality can be pictorially, you can see this X and Y, these two sets are actually not equal in general, just in our conventional set theory, but they are roughly equal. You can see this pictorially, the X lower is same with this Y lower, and this X upper is same as Y upper. So we can say these two sets are roughly equal. Now, there are several ways to define graph sets. So what is graph set? So we are going to define one relation on this power set of U. Like that, any two elements are related, they are roughly equal. So it is very easy to check this relation is an equivalence relation. So entire power set is going to partition regarding this. An element is a graph set. Means a class corresponding this equivalence relation is a graph set. So we are going to take the definition of graph set here according to this way. Now we have our power sets of U: usual union, usual intersection, usual complementation, whole set U, and empty set. So this is the power set algebra. Next level, we are having with this power set algebra, we are going to take this one lower approximation operator and upper approximation operator. So this algebra again a power set algebra, you can say, with approximation operator. Then we are going to define this approximation space algebra. Means within this we are going to define, suppose the class, we are going to define all these usual operations, means like intersection, union, within this. So I am just going to this is the class of this something. Now this typical binary operation is different from our usual union. So what about this? So this is nothing but, in this case, this will be nothing but, so this operation is going to define in terms of usual union, intersection, complementation, and these two upper and lower approximation. So this is nothing but x union y, then intersection x union x union y. So we can observe that this operation is defined in terms of usual union, intersection, lower approximation, and complementation. Similarly, we can define this operator, and we can easily prove this definition will be well defined. There is these two results are very interesting. Actually, we'll be using this result. This will be reduced to usual so depending on this fact, we can easily say that. So this definition should be well defined. So after that, we can have this approximation space algebra. And within this approximation space algebra, it is going to form one bounded distributed lattice, and that is going to actually De Morgan lattice that is going to satisfy few properties. I am coming later. So here lattice order will be defined like this, and we are calling this lattice order as a rough inclusion. So now, so this operation already I have mentioned. So now, this power set algebra is a model of Boolean algebra. Now this power set algebra with this approximation operator is a model of topological Boolean algebra. Now this approximation space algebra is a model of Piraf algebra, and the non-modal reduct of this approximation space algebra will be the quasi-Boolean algebra, or that is same as the De Morgan lattice. So from the rough set theory, so we are having this 1, 2, 3, 4 means this our abstract algebra like Boolean algebra, topological Boolean algebra, quasi-Boolean algebra, and Piraf algebra. So when my talk will be progressing, so we are having more and more abstract algebraic structure will be coming from this rough set theory. Now what is the motivation of this talk? So now we are going to L. Oh, this is I, lower approximation. So, okay, so our motivation is we are going to find such an algebra where we can have one term definable implication within that algebra. That means this implication can be defined in terms of other operators within the algebra. This is going to satisfy the property P. What does it mean? P property. This will be going to the top if and only if we can achieve the order. If in an algebra we have such kind of binary implication operator which is term definable with the other operators, so such kind of algebra always having one sound complete Hilbert type logic. So that is the beauty of this P property. So now see, okay, in Boolean algebra this implication is all we know, our classical implication. This. So we can easily check that this implication is a is going to satisfy this property. Negation. Curl. So now you can see this, if this is 1, then in Boolean algebra we have law of excluding middle. So using that fact, easily we can have this x less or equals to y, and conversely also. So next, come to this topological Boolean algebra. So this is a nothing in special. One additional unary operator is going to satisfy these 4 conditions, will be called a topological Boolean algebra, but this is the algebra actually behind the modal logic S4. Here also this implication is going to work, the same implication. Next we have the De Morgan lattice. So the difference between, why we are calling this quasi-Boolean, because you can see the law of excluding middle is missing here. Then the abstract algebra corresponding to this approximation space algebra is nothing but our Piraf algebra. So what is Piraf algebra? This is the De Morgan algebra or quasi-Boolean algebra, which is going to satisfy this property. So as topological Boolean algebra can be obtained from Boolean algebra, similar way we can have topological quasi-Boolean algebra from the Boolean algebra. Means one binary operator, one unary operator I, which is going to satisfy the same condition what in the case of Boolean is satisfying. So next, another algebra which is equivalent to this Piraf algebra, and that can be also extracted from this rough set model. Here I have mentioned if we change this union or intersection here like this x, and all these are non-Boolean, means earlier case also this is not going to class X, so that structure is non-Boolean. So here in this case, if we consider yes, okay, U. So this work is due to Lucia Iturio. So okay, sorry. So this work is going to this Lucia Iturio. In the same way, if instead of taking our binary operator, if we are considering this one, then this is also a model of approximation space algebra, and the abstract algebra is nothing but this Lukashubis 3-valued algebra. This is due to Monteiro equational one, that's why we are using the name Monteiro instead of Moisil. So here you see same De Morgan algebra, that is quasi-Boolean algebra, one unary operator that is going to satisfy these 3 properties. Again, if we lose this number 4 axiom, another algebra is going to come, that is okay. So first that is tetrahedral modal algebra. You see this from this LM3 only axiom 4 is missing here. So this algebra also due to this A Monteiro, and the reduct of this algebra is again the Benlove 4-valued logic L4. Okay, so this is also one algebra we can consider in our investigation. Before that, another equivalent algebra with this Piraf algebra, that is also coming from the rough set model. that is regular double stone algebra. So now similarly we can have more general structure than this PDF algebra. This is our system algebras. Now come to this. So here this is PRA, which is the model of this approximation space algebra. This is quasi-Boolean algebra, the reduct of this approximation space algebra, the abstraction. Then this is the topological Boolean algebra. This is Lucas-Schubitz-Montreal algebra. This is regular double stone algebra, and this is topological Boolean algebra, Boolean algebra, and this is our system 1 and system 2 algebra. Now in this figure, this downwards means we are going to have some more restricted structure. Now the question is, in which structures this always we are having this kind of term definable arrow which is going to satisfy this property P. Yes, I am coming later. Okay, I am coming later. Okay, so here in quasi-Boolean algebra and topological quasi-Boolean algebra, it is not possible to find one arrow which is definable in terms of other operator is going to satisfy the property P. That can be achieved by a very simple example. I is the identity function. So let's go back to the definition of this topological Boolean algebra. So this is one example of topological Boolean algebra. So now my claim is, here in this algebra we can't have one arrow which is going to definable in terms of other operator which is going to satisfy the property P. Now let us consider this element A arrow A. What is the possibility of this element? This element involving the terms either A or negation A or join and meet. Okay. Now in this example, negation A is A. A meet A is A. Sorry, A join A is A meet A is also A. So therefore this is always A which is not equal to 1, but A is less equals to A. So in this 4 element topological quasi-Boolean algebra or Boolean algebra, or topological quasi-Boolean algebra or quasi-Boolean algebra, we can't have any definable arrow in terms of other operator which is going to satisfy the P property. So in these two structure our search is negative. Then I am coming to PDF algebra. Let's see the definition of PDF algebra. So in this case the answer is positive. So we are having not only one, we are having 4 term definable implication operator within this PDF algebra which is going to satisfy the P property, which are, we are calling all of these arrows are going to satisfy this P property, that is x arrow y if and only if x less equals to y. So why these names are coming, these suffixes are coming? This is the first rough implication which is coming from this approximation space algebra. That's why R for rough. And this implication is going to give the full distribution property. That's why it is called this heading H for heading. And this implication is same with this implication which is used in Lucas-Stupes three-valued algebra. That's why L. And C, because we are searching all this combination, and these are the exhaustive study, and these are the all different type of term definable implication which is going to satisfy this property C. The last one is C for Chakraborty, because Sir gave us this idea to form this. Okay, so all these implication are term definable, means defined in terms of other operator, and it is going to satisfy the property P. And interestingly, all these implications are different. That means we are having the logic corresponding to this P-rough algebra with respect to each of these implications, and we are having all these logics are different. And logic means I am a sound complete, obviously, and this all these implications different. I am going to take the example. Okay, skip this example. Next. And as this LM3 is equivalent with this P-rough algebra, so here also we can have this 4 implication which is going to work. But here this regular double strain algebra is not exactly, the signature are different. That means we can say these are term-wise equivalent. So in this case also we are having 4 different distinct implication operator term definable, which is also going to satisfy the P property. Then the next question is here we have the implication one, at least one implication term definable which is going to satisfy the property P. Then obviously here already we have seen, here also we have seen. So this is our system algebra, which is a weaker structure than P-rough algebra. You see from the P-rough algebra some axioms are missing here. That's why this algebra is strictly weaker than this P-rough algebra. Still this arrow R is going to satisfy the property P in both these cases, and which is going to satisfy the property P. Then this new system of algebra. Then in P-rough algebra we are having this 4 kind of implication of term definable implication operator which is going to satisfy the property P. Now with this arrow R we are having this cluster of system algebras which is going to satisfy that same conditions. With the help of that we are having this sound complete logic corresponding all these system algebras. Then the question is, apart from this implication, is there any role to define new system algebras which are weaker than this P-rough algebra? The answer is yes. We have already one arrow among these 3. These are ongoing work. That's why we are calling it this new system algebra. So we have another cluster of algebra with respect to at least one of these 3, which is again the structure, which are structures weaker than P-rough algebra, where we have one term definable implication which is going to satisfy the property P. That means we are having a sound complete logic corresponding to those algebra. Then next, here we have the result of the investigation negative. Here also negative. Here is the positive. What about this TMA? So this TMA proposed by A. Monterio, I think in 70s. From there they were trying to search one term definable implication operator is going to satisfy the property P. But recently we have observed that yes, in TMA also we have achieved one term definable to obtain one term definable implication which is going to satisfy the property P. So here TMA not only one, also we are having more than one term definable implication is going to satisfy the property P. So now we can say we have one sound and complete logic corresponding to the tetravalent modal algebra also. And this tetravalent modal algebra, the reduct is going to this main love four valued model, this four valued logic. So anything else? Okay. So this is our algebras which we are extracting from the rough set algebra or rough set theory, rather rough set theory. So in most of this we have succeeded to obtain one binary implication operator, term definable means that can be defined in terms of other operator is going to satisfy the property P. Once we have that mechanism, so easily we can write down this this Hilbert type examination of that logic corresponding to the algebra, and that is always going to sound and complete. Thank you. Yes? Yes, matrix means? Table. Yes, yes. Yes. Yes, yes.
Questions?
Yes, but these are ongoing work, but yes.
Go ahead, ask questions because the microphone
That
is
will
not
be
working.
coming next in some papers.
Microphone's not working, so just carry on.
So I'm just curious, there's all these implications that you defined. You were mentioning satisfying some property, or by the time you mentioned it, I have already forgotten what that property means. So I'm just curious. Like, how is this implication, how are these operators relevant in this discussion? Say, this is having some property, some interesting property, but this doesn't satisfy the property. Or this, like, if you have this, you will have the other two. Something, like these kind of relevance or these kind of discussion.
If once you have this term definable implication which is satisfying the property P in one algebra, then the semantics part is very easy. You can easily check by one side the all axioms are valid, and by the other side all these corresponding rule will be valid. So that is the beauty of this. But if you say some broader question, is that the necessary and sufficient condition? So honestly, I don't know.
Can you say what? No. These four different kinds of implications, what kind of property
Yes.
will they have? I mean, she was asking for.
Property. So actually, if you consider this implication, then you can get the half side of resolution. If you consider this implication, you can get both sides of resolution. If you consider this one, another half side of resolution. If you consider this implication, resolution, usual resolution. So with respect to this implication, this if and only part is going to satisfy. with respect to this implication, the backward side is going to satisfy. With respect to this implication, the forward side is satisfying. With respect to this implication, none of this satisfied. And there is a very beautiful relationship among these algebras, among these implications, that is also like this. This is arrow L, this is arrow R, this is arrow H, and this is arrow C. These two are non-comparable, and we are going to have this relationship among these implications. So this is all work regarding this Piraf algebra, but also we did this kind of work in more general structure. So now currently we are doing this kind of work in this tetrahedral model algebra. Anything else?
More questions? Okay, so then let's thank the speaker. Okay, our next speaker is Vijit Ghosh. He's going to talk about succinct Kripke models.
Good afternoon, everyone. I'll be talking about these succinct Kripke models using BDDs and something called mental programs. This is a joint work with Melvin Gregor. These are both ILLC professors, and Haitian Wang is a PhD student in ILLC. So let's begin. So please interrupt me in between, because this is all about not that abstract thing. So this is all about complexity and computational issues. So let's begin. So I'll give you the motivation and background, and I'll spend most of the time in motivation and background only, and then I'll quickly go over what we are currently doing. Okay, so motivation going on to, so look into this picture, and if I tell you to count say how many red dots and blue dots are there, it's pretty difficult. It might, to some people, it might also appear that both are almost equal, right? But they are not. Now, if I give you the same thing in this manner, right? Now it is, the counting is pretty much easy. So the moral of this story is, representation matters. Whatever you want to represent, it matters on the complexity of counting and all that. This is a similar work we are doing actually. So before that, I'll give a quick brush up on epistemic logic. So epistemic logic follows this kind of syntax. So it has propositional connectives, and it has this knowledge operator, right? And an epistemic model is a set of possible worlds which have these relations, which we call the indistinguishable relation between agents. So these possible worlds, so for example, this is a model of an example scenario where there are three agents, A, B, C, and they have been dealt 3 cards, 1, 2, 3. And each of these agents pick up 1 card. Now, these are the scenario that is modeling what do these each agents know about what the cards other agents have and about their own. So for example, this possibility tells that A has 1 card, B has 2 cards, and C has 3 cards. And this relation is the equivalence indistinguishable relation, which is telling that, okay, since B has 2 card, card 2, then B cannot distinguish among the scenario where A has card 1 and C has card 3, or A has card 3 or C has card 1. Okay? And these are all the possibilities that can work. And how do we evaluate whether an agent, say I, knows some facts psi? So we evaluate it like if we want to evaluate from some possible world. So for example here, and we want to evaluate that whether agent B knows it has card 2, right? How do we evaluate? We evaluate like from this possible world, we consider all the possibilities that agent B considers, which is S and U. And in both of the possibilities, agent B has indeed card 2. So we can actually say that agent B knows that it has card 2. So this is how we evaluate, right? And then there's this extension called what is called dynamic epistemic logic. So you might not, we can brush over this quickly, but dynamic epistemic logic is just extension of the epistemic logic, which extends it with this operator. This is telling you that if some event occurs, and as per the event, the whole knowledge structure changes. Now, if you can reason among the knowledge of the agents. So for example, say this is called the card scenario, and this is an action model. This action model tells that A has privately told B its own card. Okay? And when you update it, there is some formal updating mechanism. This is the resultant model. This is a Kripke model, and as you can see that now A actually knows what card it has. A cannot, so B is actually saying what card it has to A, and here after it tells you, here you can see that A knows that what card it has. A actually previously it couldn't distinguish between what B had and C had. Now it can distinguish. Okay, so this is the basic idea. So what is the problem, right? Now, this is the model checking problem, right? Standard Dale model checking problem, where you are given the Dale model, Kripke model, a possible world, and you are given a formula, and you are said that whether that formula holds in that possible world in that possible Kripke model. And this decision problem is actually been proved to be p-space complete. What is p-space complete? The people who don't know, just remember that consider this problem is very efficient, okay? So like computationally efficient. To decide this, a computer will take polynomial space with respect to the size of however these are interpreted. Okay, so just consider this as efficient, okay? Some small space will be taken by the computer while deciding this problem. And that small, how do you calculate that small? It is with respect to the size of this model and formula and all. Just that. Okay. Now, what is the problem, right? We are given the Kripke model. Now, let's just zoom out. Okay. Let's just say that now we are given how many propositions there are in each possibility. Say n, right? We are given n. So, for example, in the card scenario, say you have been given 4 cards, right? Now, how many possibilities there can be? It will be huge. Like as per with respect to the previous when there were 3 cards dealt, now it will be huge. So when you zoom out of and you look only in the propositions, say there are n many propositions, the worst case Kripke model it can result is 2 to the power n. Now, as per how big the Kripke model was, the model checking problem is very efficient. It's taking small space. But small space with respect to the Kripke model, size of the Kripke model, not a small space with how many propositions are being used. So the question is requirement. So what we now require is a succinct representation of the input itself. So we want to design so given a Kripke model, we want to come up with a very succinct representation of the Kripke model, where this size doesn't explode with respect to the propositions that has been used. So in this line of study, 2 main studies have come out in like 2018. Okay, so before that, I'll just show you exactly what we are trying, what these approaches are solving. We need what? For every Kripke model, we need a representation, say rep. Okay, and this what are the properties this rep or representation of the Kripke model should follow? With n propositions, size of the representation of this Kripke model, which we should be significantly lower than the exponential 2 to the power n. Okay, and this is the main part, this, which is the model checking should be in p-space with respect to that small representation. It is not like, it won't be like you are given the previous algorithm, say MC, okay, which took the actual Kripke model and phi, and this was the, and used to tell it yes or no, right? And this was the actual p-space algorithm previously, right? And now you cannot do like, okay, I have a representation of M, which is an equivalence representation. I make it into the previous Kripke model and then run. No, this is not done, right? If you do this, then again the similar problem occurs. So you have to come up with a model checking algorithm that is still in p-space, but with respect now to the respect to the size of the representation, small representation. Okay. Now the first approach that has been brought out in 2018 by Van Bentham and Malvin, and I think Kylie Sue was also there, is which is called the knowledge structure. Okay, so I'll explain what a knowledge structure is with this example, but before that, as a formal definition is this. So the knowledge structure is this triplet, V, theta, and O. V is the propositions that have been used, the propositional letter. Okay, theta is a propositional formula, and it is just saying that, okay, all the possibilities that you form out of these propositions in V, theta should be a common propositional formula that should satisfy. Okay, and O, here O is for each agent OI, which is actually a subset of V. This is telling you the indistinguishable propositions, or what you can say that in simple terms, you can say that the agent I can actually observe these propositions. I'll come to that. What do you mean by that? By this example, you see this Kripke model, it has 4 possibilities. So this Kripke model is based on 2 propositions, P, Q, okay? Here, both P and Q are false. Here, only P is true, Q is false. Here, Q is false, Q is true, P is false, and here both P and Q is true, okay? A cannot distinguish between these 2 and these 2. B cannot distinguish between these 2 and these 2. Now, how do we represent this model using this knowledge structure? Now, what the V will be? V will be simple P and Q. Okay? Okay, what is the theta? So, given P and Q, these are the only possibilities that you can actually form. So, theta is a true. So, no propositional formula, everything true. So, the theta true being actually, theta is being satisfied in all of these things. If you wanted theta to be P, only these many possibilities should have been there. Okay, so theta is true here. Now the OIs, right? Now here are so how do we W? So the W is here. All the evaluations where S satisfies theta. Now OA and OB. Here it is telling A can actually observe the proposition P, which means A can distinguish the valuations of P. Here, since it is telling OA is P and OB is Q, as you can see, it is because of this. As you can see, the words, the possibilities that A cannot distinguish among, has common valuations of P. So here P is, both of them P is false, here both of them P is true. Similarly, if OB is Q, means B can actually distinguish what value Q will hold. So this is actually B. Here, in both of the cases, Q is false. In both of the cases, Q is true. And it has been shown, and it is actually, you can, if you are familiar with Kripke models and how Kripke models, especially in the S5, like the equivalence thing, how they are being interpreted, you can actually see that any Kripke model can be represented by these structures. Now, what is the advantage here? Okay, here is the formal definition. How do you calculate the RIs here? So, It should these S and T, those two valuations will be related if their intersections are common with the observable propositions. Okay. Now the main thing here, so you are given n propositions. This is telling the size of the knowledge structure will be very small. In other words, who are not getting this, this Cn, C is some constant. In other words, who are not getting this, say you have been given V, right, of n propositions. And the worst case Kripke model size can be 2 to the power n. So some say, forget 2 to the power n, say you are given V, the worst case some m size. So you are given V, which is n many. Worst case model from this, same V, some m. Now, say you are now given some V prime, which is of size n plus 1. Okay? The worst case Kripke model with respect to m will be twice. So the worst case Kripke model will go twice, right? And this is how the blow up occurs. Here, if you add one more proposition letter, the worst case knowledge structure will be n plus 1. Only linear mean, right? So, and also, in addition to that, so we have left out, I have left out for the time being transformation from action models, but action models are just Kripke models again. So this is a similar representation for action models as well. Now the main claim has another one. So the second claim, which is it has the model checking has to be in P space, and P space with respect to this size of the knowledge structure. How do we do that? What they do here is using BDTs. So what they do is, so given the phi, so in model checking, these are the three inputs, right? You are given model, you are given formula. So given this phi, and in Kripke model, you are given an S, a possibility. So you are translating now the input formula, phi, with respect to M or F, whatever you call it, into a Boolean formula. Okay? And the correctness is this. So this Kripke model, this pointed Kripke model should satisfy phi if and only if the valuations will satisfy this translation of phi with respect to F. I'll come to a very small example, is how do we translate, say, Ki phi with given some F, okay? Say, so this F has been represented in that knowledge structure thing, right? Now how do we say, this is actually saying, so how do we, so given this Kripke model, right? How do we evaluate Ki phi here? We look for phi in each of them, right? Yeah. Yeah. Oh, I have 5 minutes. I was okay. So we look for phi in every each of them, right? This is actually saying that only, right? This is actually saying that only. So OI are all the observable variables for agent I. It is saying for all the valuation except for the observation variables of I, check if that possibility is satisfying theta. Theta is the world law. So if that possibility is satisfying theta, that is the possibility exists, then the rest of the translation of phi should satisfy there. This is asking. Now some people might argue here that this is not a Boolean formula, but I argue this is actually a Boolean formula. Since V and V not OI are finite, you can AND them up, right? Now another question might occur that if you AND them up, this will give you a huge blow up. But again, from the space perspective, this isn't giving you a huge blow up. Why? Because it's space, it's not time. Space can be reused. So what the computer or the model checker will do, with respect to one evaluation, it will check this formula. Again, it will go to the next evaluation, it will check the same formula. And while going to the next evaluation and checking the same formula, it will reuse the space of the space used by the first formula. That's it. So with respect to space, it isn't much. It isn't blowing up. So this is the first approach. Now I come to the second approach, which is the mental programs. This I'll brush over because I have not much time left. The mental program is another approach introduced by Shariar in 2018, which is a very regular expression looking thing. So So mental programs is actually used to encode any kind of relation. So this is saying, so this is a syntax. I'll show you what it is saying. This is saying that two evaluation S and T are subsets of V. S and T can be related by P assigned to true. It is saying that P will be assigned true, which is T is equal to S union P. Similarly, P is assigned to false. T is equal is T is if S has P in it, T will take away P from it. Beta is the PDL-like test. So it will say that okay, S and T are same valuation and both of them are satisfying beta. And beta is actually a propositional formula. Pi 1 plus pi 2, most of you might have like guessed, either S and T is related using pi 1 or S and T is related with using pi 2. Intersection and then there is concatenation, which is saying there will exist a middle valuation U such that S pi 1 will take you to U from S and pi 2 will take you to T from U. Okay? Now, what is the succinct model? Remember what actually is a Kripke model, right? The Kripke model is actually a relational structure, and these pies actually are able to encode any kind of relation that you can imagine, because pies are actually they are actually relation among the subsets of V. So for each agent, you just give a mental program. So like for example here, it is like this. Pi A is either assign Q to true or assign Q to false, right? So pi A is either assign Q to true, or assign Q to false. And pi B is either assign P to true or assign P to true or assign P to false. Here is also. I don't know if you can notice, so in that paper also, they have proposed a model checking algorithm using this approach, and it has been proven to be p-space. They have given a theoretical game. The problem is they have not implemented their mental program thing. Yeah. Intersection? Yes, so nice question. Actually, we didn't find any argument where we don't need that intersection, but the thing is, intersection is helping us actually. So what you can do is you can go around U union and you can get a negation. So you can give a pi inverse. Okay. Now, as you can see, this looks like regular expressions, right? So if you want to take the automata approach, pi inverse is a bit complicated. It can blow up. Intersection, as it turns out, in NFA form, you can try product construction. So no, actually no. In the p-space hardness proof, they used intersection. So yeah, this is not the source of complexity. So there were many other extra formulas like inverse and assignment of other formulas also. But we proved that okay, these are all equivalent. We can be represented using some combination, and they are small very. So no. Yeah, but yeah. So they have proven a p-space thing, but they have not implemented it yet. Okay, so one thing those who have kept attention might realize that mental program and knowledge structures are kind of dual to each other. Knowledge structure is actually saying what not to change. Mental program is saying what to change. So for example here A, it is saying that what to change, Q to change. Remember the observable variable of A was P, what not to change. So these are two dual things. So from here, the main motivation of our work started. First one, implementing mental programs using BDT. So this is how we started with the thing. Then the second thing is that we are trying a comparative study between mental programs and knowledge structure, because we have been able to found some knowledge structure whose mental program is huge. Also, we have been able to found some mental programs whose knowledge structure is huge. But the problem is we aren't able to get any lower bound technique, because we need a new technique here. So we are not able to get lower bound technique. Okay, we have a knowledge structure some F, and we are getting a mental program. Okay, pi is huge with respect to F, but can there be smaller mental programs? What is the guarantee that there cannot be any smaller mental programs? These are the techniques we are looking out right now. Okay, so yeah, as I was saying, a mental program with a large knowledge structure, we have, and also we can find a small knowledge structure with large mental programs. Okay, so also we have extended not for S5 only, we have extended for any relation. So you go through any relation. Okay, so one approach is we are trying out now mental programs to BDDs because knowledge structures have already implemented because they have been like evaluated on Boolean formulas, right? So BDD are very formal and popular packages, so they have been implemented. But we are trying to implement mental programs to BDD. The brute force approaches use this, like, so you turn a mental program pi into a Boolean formula that is over V union V prime. I'll show you what V union V prime is. So let's say V is PQ, V prime is a copy of V, so P prime Q prime, that's it. P prime Q prime. So what we do is, we tell that V to be whatever propositions that are supposed to be true in the source evaluation, and V prime to be the whatever propositions that are supposed to be true in the target evaluation. Okay. For example, I'll give you. So for example, take this one, right? P is assigned to true. What was the semantics here? P is assigned to true was, you can relate P assigned to true to T if and only if T is equal to S union P. So the only thing changed in T is you include P. If there was P from before, all okay. If there was not, you include P here. That's it. And this is the thing. It is saying that in the resultant state, P prime should be true, which is a representation of P in the resultant state. And for all the propositions that are not equal to P, whatever valuations was there in previously should remain as it is. So this is and there are more complicated things for the inductive behavior as well. So this is a brute force approach. Another approach we are trying out is the automata approach, as I told you. So mental programs are like automata, right? And we are trying out this, but the problem is the brute force evaluation, even with intersection, as I told you, even with intersection gives you blow up. Why? Because what it is, like, as you have seen in this syntax, the basic things are these many, right? These are the, if you think of the entire thing as regular expression, these are the basic alphabet. Now if you take it with the basic alphabet, if you take it the assignments, as you can see, the path will take you along every evaluation, if you can imagine. Like for example, if you want to take P is assigned to true, then Q assigned to true, then Q assigned to false, right? This will take, so in its entirety, this is actually not required. But that automata will take you through this. So ad hoc, so a straightforward brute force approach won't work here. So now another thing we are actually trying to prove. So however way you want to take this translation through automata, you won't be able to succeed. That's another lower bound technique we are trying to prove. So yeah, this is all I have. So if anyone have questions, just yeah, thank you.
Okay, questions?
Huh?
Normalize these in some normal form. I mean,
Okay,
so
so
that's something
we
like
try
that you
to-
surely don't want, right? I mean,
Yes,
but that you
because
can easily try a normal form to get.
we
rid of
tried
these.
to. There in normal form, intersection is actually creating a problem because you can concatenation you can get inside. Clean star is not there, but intersection you cannot get concatenation inside. So in that case, if I can get concatenation inside in some way, the Boolean formula will get an implication form. So if there is a test, then do this. If there is a test, then do like that.
Any more questions, comments for the speaker? Okay, so then let's thank the speaker again. Okay, our next speaker is Sneha Shamanto. She's going to speak on zero laws in modal logics for graph games.
Hello everyone. This is based on joint work with Shweta Ghosh, Saurabh Chakraborty and Vijit Ghosh. Today I will be talking about 0-1 laws in modal logics for graph games. So first I will be talking about graph games. We all know about graph. It can be directed or undirected, or it can take parallel edges or loops or not. As a graph can model different network channels and communication channels, so graph games can describe different scenarios, so it will be interesting to study. So we will be mainly focused on games which are 2-player and zero sum. It means one player's win can ensure that other players lose, and vice versa. And the players have perfect information about the game. Both of the players know all about the graphs, all information about the edges and their current positions. For 2-player zero-sum game with perfect information, we can think about as example, we can think about chess or tic-tac-toe. So I will be talking about some. There are mainly 4 types of graph games. One is traveling game, where 2 players have to traverse to the graph, and if one player gets stuck in the graph, they lose. Or there are travel and damage, where one player has to travel and one player plays as an adversary and he tries to destroy the links. And there are some games which is meet or avoid, where the one player wishes to meet the other players and one tries to avoid the meeting. And there are occupation games where both of the players while traversing, they occupied the vertices and they colored the vertices with their color. And if one player, if he is forced to enter other already occupied vertices by the other players, or he cannot move further, he loses. I'll be mainly talking about one of these meet or avoid game, which is widely known as cop and robber. And here there are 2 players, cop and one is cop and one is robber. And from the name, as you can see, that robber tries to avoid the cop and cop tries to catch the robber. First cop in this game, first cop chooses a vertex, then robber chooses a vertex accordingly to start, and then they take turns alternately and they move through the available edges from their current vertices to adjacent, one of the adjacent vertices. Cop wins if he can catch the robber. It means if he can reach the same vertex as robber, and robber wins if he can ensure that he can infinitely, in an infinite run, he can avoid the cop. This game is not interested in the graph with parallel edges, as it is not required if they have 2 ways to move from one vertex to another. So we can think of the graphs to not have parallel edges. For example, in this graph, there are 2 partite sets, one is A and one is B, and in this graph, if cop chooses any of this partite set and if robber chooses to stay in the same set, then he always have a winning strategy. For example, if cop chooses the point A2 and if cop chooses the point A4 and robber chooses the point A2, and then whenever the cop moves, the robber can, in the next move, he can immediately choose to stay in the same set and avoid the cop infinitely, in an infinite run. So robber has a winning strategy in this graph. And for example, in this graph, here cop has a winning strategy, as cop chooses any of these vertices 2 or 5, and robber, whichever vertex robber chooses, he gets caught immediately after that. So cop has a winning strategy in this game. So we want to know when the graph size increases, if any of this player gets any advantage in this game. So before going into that, we'll first discuss what is 0-1 law in logic. For a logical language, it satisfies 0-1 law if the probability of a n-size structure satisfying that formula, if we take it as take this as mu n phi, and if we take that limiting value as mu n phi, it goes to mu n phi as mu phi goes to either 0 or 1 for any formula in this language. So if we can see that for any formula, when in the size of the structure increases, it either almost surely holds or almost surely fails. For first order logic, it is proven that first order logic sentences with finite relational vocabulary 0-1 law holds. And for modal logic, as we know that as we can see that the translation into for modal formulas, in basic modal logic formulas into first order formulas, and through this translation we can see that 0-1 law also holds there. Okay, for example, if we take these formulas, we can see that for the first formulas is a sentence with relational vocabulary. In this case, mu phi is 0, and second one is not a sentence. For this case, mu phi is half. And if we take functional symbols, it may not occur it goes to 0 or 1, and we can see for this formula it goes to 1 by e. So it is not natural to hold always. And for a graph, the first order logic formulas holds if it is true, if and only if it is true in a random graph GNP, where GNP n is the size of this graph and p is the edge assigning probability, and p is constant here. And as n goes larger, this any formula which is almost surely true, first order logic formula, this holds there. Sorry. And these are called extension axioms. We take these axioms, we can describe these axioms as it, if we have a set of m vertices, we can, if we have a set of n vertices, we can take any m of them, and we can extend it as we can choose any m of them, and it will be adjacent to those m vertices, and it will be not adjacent to the others. So we can extend it any way as we like. And they are almost surely true, and it is shown that these formulas actually gives the axiomatization of this almost surely true formulas in first order logic. This is for one binary relation, and similar formulas actually axiomatize the first order logic sentences, which are almost surely true. So, as the question we are asking, that for cops and robber game, that we can see that robber has to avoid the cop. So if we can ensure that wherever robber is, he can avoid cop in the next move. So if we can do this at any point of time, then he can, in an infinite run, he can avoid the cop. So if we take this formula, that for all x, for all y, where x is the robber's position and y is the cop's position, there exists a z which is adjacent to y. That means sorry, there is a mistake. Actually y is the robber's position and x is the cop's position. Y can move to cop can move to the z vertices z vertex Z, and robber can move to the vertex Z, but cop cannot move to the vertex Z in the next turn. So robber can avoid the cop. And as we can see that these formulas are similar formulas as we have seen the extension axioms like. So these are almost really true. So we can say that when the graph size increases, robber has the probability of robber having a winning strategy increases and it goes to 1. And in random graph in GNP, as n tends to infinity and p is constant, that robber has a winning strategy with probability 1. And similarly for we can show that for k cops and 1 robber games also. Now we'll come into the logic of 1 cop and 1 robber. It is actually known as logic of hide and seek, and cop and robber is as we describe the game as cop and robber, so we'll say about this. In the language there are two set of propositional formula, one for cop and one for robber. As in modal logic, we don't have and we have natural model as graph, and we have to keep track of to move of these two players, cop and robber. So we have two modality here, one for cop and one for robber. And to describe the point where they are in the same vertices, to say this, we have I. So two disjoint set of proposition variable, one is C and one is R, and P, that PCs are coming from the C and P are coming from the R, and we have I. So in this logic we can describe that if robber can avoid the cop in kth turn or cop can catch the robber in kth turn, so many things, such things. In this formula we can see that for any move of robber, for all move of cop in k turns, after k turns of robber and after k turns of cop, there is negation I. That means they are not in the same vertices. So robber can avoid the cop in kth turn. And we can extend this to say that in this formula, if we take this formula, it is saying that if they start from two different vertices, then robber can avoid the cop in a k move game. The model of this logic is similar as modal logic, and the V is the valuation function and R is the accessibility relation. Here for the pointed model, as in modal logic we have to take one world, but here as we are taking two different players, we are taking MST, two different state. And the semantics is as follows. For propositional variables, when we are taking the proposition from C, we will check it for the position of cop, and for the when we take the propositional variable for the set corresponding to robber, we will take the formula. We will check the formula in the position of robber. So that is for T, and that is for C for the cop. And the usual and negation is there, and it will I will hold when S equal MST will satisfy I when S equal to T, and MST will satisfy boxy psi when there is a world S prime which is accessible from S, and in ms prime t it satisfies psi. And similarly for the modal operator corresponding to robber. And we will say the formula is valid in a model when for all s and t it holds that mst satisfies phi. Okay. Okay. Now that okay, for this logic of cop and robber, one cop and one robber, 0-1 law holds. It means that as we described before, the probability of phi being valid in a n-size model goes to either the limiting value either goes to 0 or 1 for any cop and any formula from this logic. We can verify this easily that if there is a translation from cop and robber logic of cop and robber to a faster logic formula, which is as follows: that for any propositional variable we will take a unary relational symbol, and for usual and negation it will follow, and for I it will x equal to the formula will be x equal to y, and for box C it is as follows. Similarly, as we have seen in modal logic, and a formula is valid, and the model also translated into the usual interpretation of this relational unary relational symbol as the valuation function, and the binary relational symbol as the accessibility relation here same, and this a formula phi will be satisfied in this in the corresponding LCR model if and only if that for all x for all y translated phi will be satisfied by in the faster logic model. And from this we can show that 0-1 law holds in this logic of cops and robber. Now the question is that in faster logic in faster logic it is shown that to check for a given sentence with relational vocabulary, to check it is shown as p-space complete, but the model in the modal logic, for modal logic case it is p time. So we are checking that what is the case for what is happening here, that where it lies between there is a huge jump, so where it lies for the logic of cops and robber. And we are also trying to get the axiomatization for the almost surely valid formulas of this logic. Okay, I will skip this. Okay, let's say so in the algorithm where to check for faster logic, it is that it is an alternating algorithm. There are some universal state and there are some existential state. For in this algorithm, they have taken the description of a variable of in terms of some, say for the variable xm, they have the description is they have taken an individual description as dxm minus 1 x1 dxm in terms of the set of variables x1 to xm minus 1, as that they have taken all atomic formulas containing relational symbol, and they have taken that how they are related with the existing variable x1 to xm minus 1. So these are called individual description. As we have seen that for faster logic formulas which are almost equally true, they can be axiomatized by those extension axioms. So they have taken, similarly, they have taken these individual descriptions, and while they are checking for a formula, they are taking, whenever there are any quantifier, when they remove this quantifier, they take a new variable, and they give an individual they give a description of this variable with already existing variables. So they update the descriptions, and after removing all those quantifiers, it is just checking those formula if it is it holds by this description or not. So for now we have shown that we have constructed a similarity model which is as a random model for a where we take for any world we take the proportional value of a proportional variable with a constant probability half, and for any accessibility relation we take any pair of worlds in this relation set with probability half, and we say this as a random model, and we take Rm in as n tends to infinity, and we can show similarly that a formula is almost surely valid if it holds in that Rm. And we have get a set of formulas which are this, and with the already proven axioms of LCR minus I, that we have shown that if any model satisfies these formulas, it is bisimilar with respect to the random model, and we are still far from showing the complete, these are the complete axioms, and what are the complete axioms of these almost surely true formulas from logic of Cox and Robert, and we are checking for the complexity class. Okay. So in this logic we can, as we have seen that we can express that in K moves if Cobb can have a winning strategy or Robert can have a winning strategy, but it is still unable to express if one of the players has a winning strategy in infinite game, as we don't have any infinite formula in this case, and we are still and if from the 0-1 law in this logic we can show that for a finite game Robert has a winning strategy almost surely. Thank you.
Questions?
Capron and Halpern do show a 0-1 law for modal logic, right?
Yes.
Can't you use that to prove the...
No, actually for the I can take it as a propositional, can take it as a propositional variable or any other thing, so I cannot extend that. I was trying in that way also.
I see.
The algorithm cannot be extended.
The translation that they give
Yes.
into the random graph for any multimodal logic, so you can't do that translation, no?
No, they actually have shown this by they have used a translation from modal logic formula to a propositional logic formula that by which they can. But I can do that for this I. Without I can. It is possible, but with I it's not.
I see. So this is one thing, and the other is the comparison with first order logic. I'm not sure that that's particularly useful with the grand gene algorithm that you are saying, because
I was trying to say that if the translated formula is a special case, so if this is getting any advantage in this case, I can reduce that.
okay. I mean, mainly because, see, the thing is, 0-1 law for first order logic doesn't imply because you have a translation into that, right? Because the translation is into submodel, into
Yes,
a
yes.
restricted class of models. So as size increases, you can't tell
But
whether.
if the model have a 1-1 correspondence, so I can say that.
Not clear, because it's still all bisimulation invariant models, no? So as size expands, you have to see. That's why Capron and Halpern have to reprove 0-1 laws.
Okay.
So you need to do that. So I'm not sure that that will actually help you. So you have to do something. Whereas, I mean, what they are doing is much closer to what is going on here. But that is one. And the other is about player having an advantage, right? I mean, either player having an advantage, right? Now, I don't know whether that has much to do with the size of the models, right? It has more to do with the graph structure.
Density of the graph kind of thing.
Right.
If there are more edges or.
Well, over the same vertices, if you have more edges
Yes.
in a graph, then of course players will have advantage. But if the graph itself is expanding, right, then it's not clear. So that is, I understand. If over the same vertices, if you have different sets of edges, of course one player has more advantage.
Also, if you increase our vertices, there will be more options to increase the degree as well.
That's true, but
As the
it will
edges
happen for
in-
both, right? I mean, as n tends to infinity, you're not good. Nobody is going to have anything.
The age assigning
So you
cross
need some way of
probability
growing the
constant
graph,
also.
like we do generally in graph theory. We talk about both, augmentations and expansions, right? So I'm saying here, if you're looking at augmentations, as n tends to infinity, surely you will expect that one of the players will have an advantage. But if you have only expansions, why would you expect? And so this is you get the point of what I'm saying, right?
But so what tagging is also telling, like if you have an n-side graph, if you try to include one vertex and you try to increment that graph in any way possible, it is okay. So what we will be able to find is like in most of the way that is possible, the playable Kn, the Robertson Kn.
Okay.
Because at some point of the time, the more the degree increases, the more advantages it gets. Now again, you put on another vertex.
So this is a question that you can simply ask in graph theoretic terms, right? I mean, without the logic and the what would be the?
We can look at it from a graph theory, like a random graph.
Yeah. So and see what.
The 0-1 law for that logic will have, it's like you can verify whether as the model increases, which is actually
Yeah.
the graph where the Cox and Roberts are doing, as the model increases, whether you will have more graphs when the Cox by the Robert gets an advantage.
Right.
That's what the 0-1 law is.
Sure.
Because as the model size increases, the degree also increases.
Yeah. So that's what I was saying. That I expect from the Capron-Halpern result anyway, right? But that says for any model property, I expect it to be true. So, okay. Anyway, we should think about it.
Okay, more questions? All right, so then let's thank the speaker. Okay, so there is a small announcement. I don't know whether it should be classified as small, but anyway, there's an announcement. The last talk that we have on the schedule today, it has been moved to tomorrow. So we will have one more talk after the tea break, which is going to be now, and then we will break for the day. Okay? Okay, welcome back for the last talk of the day. The last talk is by A. Mani, and she's going to talk about mereological methods for education research. Over to you.
Yeah, thanks. And so I'll be speaking mainly about, I'll introduce what mereology is, and then speak about a few applications to education research. And these are part of my recent research work in applications of mereology and rough sets to education research. So this is the abstract, and I'll try to cover at least some of it. Okay. Okay, so mereology is of course the study of parts and wholes, and those closely related to it, such as is a part of, is an integral part of, is an essential part of, and so on. And even is in contact with can also be seen as a topological relation. So these are some examples, and they can actually be used to organize knowledge in a number of non-equivalent perspectives and adapted to handle soft ideas. And as far as applications are concerned, they're used heavily, for example, in biological classification and in other and in other sciences. I'll come to that slightly later in another slide. And it's of course, while it is used heavily in higher research, it's hardly used in school situations or even in school science in a proper and structured manner. So that's why I've been considering applications of mereology to education research. And so it's necessary to explain the problems that its adoption can address and the ways it can be done. And as far as the subject is concerned, it has a very long history. For example, it is part of almost every school of philosophy in the world. And but modern mereology is quite different from what was done earlier. And modern mereology approximately starts from around the 20th century only. It's as recent as that. So that's how the subject is. And that's why I say that formal approaches to mereology are of more recent origin. And there are a number of books on mereology which address both the formal approaches and also the philosophical ones. For example, there's a handbook of mereology available that's quite huge, and you'll find plenty of material in that. And there are many formal theoretical approaches too, and people differ on what axioms should be really used. And of course, if you try to formulate logical models for all these cases, you'll get entirely different things. Okay. All right, this I already said. Oh, this is the connection between mereology in the sense of Lesniewski and set theory. So I won't discuss this much. I'm skipping this.
You are not going to show us the previous slide?
This
This one? What is this plural discipline?
Yeah, it's a plural discipline in that most people don't agree on the axioms. For example, when it comes to the parthood relation, some people will want transitivity, while others will not want it at all. And yeah, it's okay. And of course, it's used everywhere. That's what the slide says. And of course, in rough sets, I've done plenty of work using mereology, foundational work. So this Yeah, and one point which should be noted is that a number of conceptions of emptiness is possible. And that is one thing that I'll be using in this talk. Well, I won't really bother about the other parts. So this is one way of looking at mirrorology. Say P1 is just reflexivity, then we have antisymmetry, and transitivity is totally optional, and even antisymmetry is sometimes optional. And then there is the identity definition, which is if A is part of B and B is part of A, then A is the same as B. So the interpretation of A is equal to B is read as A is the same as B, in one sense. And by ground mirrorology, there is a system called ground mirrorology, and that has first order axioms, and that includes P1, P2 and P3. That is one of the most basic systems. And for rough sets, I don't use ground mirrorology because I don't use the transitivity axiom in a compulsory way. And generally, theories that start from ground mirrorology always assume a lot more. That's how the formal theories are built. And there are several formal theories, again, for example, from an intuitionistic perspective and others. So, and these are about controversies associated with the part of relation. Say, is a blood sample a part of the person? And one has to really argue about that. And then is a lost hair a part of the body of the person? And body cavities are part of a body. And so we have immaterial parts of material objects. So these kind of issues arise at the interpretation level. And that's a good thing, definitely, and it's definitely used in biology. When we construct ontologies, these are all used.
You would like it to be a part of the person so that you can test and say,
Yeah.
my blood or his blood, right? But what about at the level of molecules?
Yeah, molecules.
Because molecules, I can't distinguish, I mean, hopefully, his molecules and my molecules,
Yeah.
right? So
those-
at what stage do you say, identity?
Yeah, it's
and
controversial. There are many views there. So it's that way. And so parthood statements are complicated both by ontological vagueness and by epistemic indeterminacy. So that example explains this. And you can ask further questions like, is water a part of a cell that it is in? Which is the molecule question. And the cell requires the water to function properly. So the water is a part of it. And the water volume is inorganic and does not require a biological process for its production. And so it's not part of the cell. So one can argue in both, in any way one wants to. And as far as meteorological predicates are concerned, some common ones are like is bigger than, is smaller than. Then we can also speak of being composed of, being an ingredient of, and being connected to, I already mentioned. And interconnections are common between meteorological predicates in specific contexts, and there are a number of results relating to this. So in formal languages, people do prove a lot of connections. And one, therefore, often one can start from different predicates as the basic ones. For example, having overlap, maybe one thing overlaps another can be used instead of is a part of, for example. So one, it depends on the situation. And yeah, okay. And in school and college level mathematics, not much attention is usually paid to the interconnections at all. They are sometimes mentioned vaguely, but not really a central part of the curriculum. And as far as STEM is concerned, these are some examples where mereology is heavily used. For example, in AI/ML practices, compositional representations are used to reduce the complexity of models of complex synthetic environments. And approximate part of relations are useful in identifying recurring parts, for example. And of course, mereology is heavily used in approximate reasoning, especially in rough sets and granular computing. There are plenty of papers due to me, and of course, in mathematics proper, we have mereology being used in the foundation of mathematics, and they are still being used, and there are many interesting problems in the foundations. And then they are used for point-free geometry, then mathematics of Wegener that I already mentioned, and other parts of mathematics. And in life sciences, it's heavily used, and also in cladistics, which is the study of classification, in biology especially. It is basically, you know about taxonomy and nomenclature in biology. Cladistics is the more modern version of that. And so that's how it's done. Entities with a common ancestry form a clade. And related hierarchies lead to the best way of classifying and naming living and partly living organisms. So that is the modern way of doing it. Previously there was a different thing. This is about, that's what I just introduced mereology briefly. And I'll go to what are the reals in school mathematics. So in the learning context, many kinds of assumptions are common about the real numbers, and these are not necessarily mutually consistent. And so it's not possible to have a single model of the mistakes. And rather a consistent model with additional predicate should suffice. That is my view. And determining the most appropriate one requires one to navigate the literature on the subject of education research, not just of school math textbooks. And the final proposed model is, however, based on optimal conditions on the language mentioned earlier, or I didn't mention. Anyway, it's fine. I'm skipping something. Yeah. This is the first statement, which says that the real numbers are taught in certain languages with much interspersed vagueness in middle school, for example. And there are many textbooks on this actually, which show how vague the language is. And there are many textbooks, and if you want the references, I can give it to you. Then further, mathematical problem solving methods and concepts have vagueness in related discourse. And it's of course possible to formalize different fragments in many ways using predicates of rough sets and mereology. This is an assertion, this is a 2022 paper of mine where I argue that mereology combined with a language of approximations can potentially be used to build higher order formalizations of concepts that go beyond the restrictions seen in that paper and in earlier work. So that is a paper which was written by Ramakrishna and others. Yeah. And however, there is much work on pragmatic approaches to the ontology of real numbers in the context. They serve as sources for building viable models. So, and then these are some problems which are found in teaching practice, which is teachers may use phrases such as plug in a value to evaluate a function and cancel instead of dividing by the common factor. So these are examples of sources of weakness. And these and the overuse of pronouns can obscure meaning of the procedures and concepts being used. So, and learning from errors can be a productive exercise. And there are several papers on this. For example, that's one, Borassi, and the use of imprecise, loose language and unidentified errors by teachers can be counterproductive, and this has been shown through empirical studies. So that is what that paper is about. And these and related studies additionally motivate the need to build reasonably formal models. I say reasonably formal, not exactly formal, to study teachers' knowledge of content and more so for the purpose of building intelligent aids for teachers. As of now, no ML model based on numeric simplifications are proposed at the level. This is the situation.
What about the second point, overuse of pronouns?
Overuse of pronouns, say in textbooks.
Math textbooks?
Yeah, that can be problematic.
No, I don't see.
Yeah, these are pointed by many authors through actual examples in textbooks. So now immediately, okay, I'll come to that. There's a book by the AMS series which deals with that. Okay, and there's a statement from that. So they want, this is the idea of coherent formalizability, which is not exactly formalizability, it's a soft form basically. By coherence we mean the formalization of disparate elements that hangs together as a meaningful whole. And the classroom discourse includes many parts pertaining to definitions, visualizations, representations, conjectures, and so on. So this means that multiple meta-level language models should be considered for the process. This is, and we don't find formal models in that paper, and this problem is partly addressed in some of my earlier papers, and through the machinery of partial algebraic systems, mereology, and general subsets. So I come to the vague reals. So this is an attempt to formalize parts of it. From the algebraic perspective, primary and middle school students typically learn subsets of the real numbers over a permissive implicit model with a very long signature. And that signature looks like this. There are so many operations, and I am distinguishing between binary negation and binary subtraction and the sign minus. So there are two symbols here, minus and yeah. This is unary while this is binary. So I'm distinguishing between those two, and even this is regarded as a basic sign rather than as a derived thing, even though it's defined that way.
Even these are in textbooks or these are your?
This is in my paper.
Your understanding. This is your understanding of the.
Yeah, it's my understanding.
Present ways of teaching in schools.
Yeah.
So your criticism or understanding.
Yeah. Right.
Okay.
And and one can further note this: the standard conception of terms in universal algebra is partially split into a number of concepts such as multiplicative terms, binomials, monomials, rational fractions, and fractions in school algebra. While from a universal algebraic perspective, all these are just terms. Yeah, and of course. Yeah, and the concept of variable is used in a loose way without a clean specification of the domains in school textbooks. This often happens. And the predicate less than is used in the sense of being numerical less than and is additionally interpreted as a transitive parthood. So this happens this needs examples though. And functional non-transitive parthood is common in problems and activities. And by functional parthood, this is an example. 3 is the greatest prime less than 5. And 5 is the greatest prime less than 7. However, it is not that 3 is the greatest prime less than 7. So this is the greatest prime less than. That is seen as can be seen as a parthood predicate. And here this is an example of a functional parthood predicate. Functionality is in the philosophical sense, not in the mathematical sense. That means there is some parthood plus some function. And they may be completely combined. You may not be able to split them. So it's that kind of functional. That is that. So that's so this is non-transitive, and that's an example. And such parthood predicate should be kept in the companion model to avoid complicating the concept of vague reals further. So what I'm proposing is almost 2 models for the situation, so that they can be integrated for interpreting the whole situation. And so relative to the formal signature, partial algebraic systems that are taught to middle school children are related to that, where X star is a subset of the set corresponding to the algebraic closure of the union of algebraic numbers and pi. This is a deduction. Yeah. And the signature I've already mentioned. And yeah, that's how it is learnt. And one can associate axioms like all this, which are pretty clear, and people may understand only part of these. That is one thing which should be noted. And so we have axioms. Yeah, all these are pretty clear what they mean. The only point is this is a unary one, and this is binary. Okay. So these are examples of admissible axioms, and that's it. So yeah, and so those are examples of axioms. One can form different kind of systems, and from those, that's the point. And it's not that every student understands or assumes all the axioms mentioned above simultaneously. And it can be expected that these are partially ordered in distinct ways in the context of problem solving. And moreover, only certain subsets. So this means a higher order approach is necessary, this previous statement. And only certain subsets of these and variants may be understood as the basic axioms. And and from the basic axioms, only certain subsets of derivations may be used, and further alternate conceptual axioms may be assumed. So that's how the situation actually is. So next I move to other problem, which is so that's about how to deal with the real numbers to start with, and how to integrate mereology with it. So that part I didn't go into the companion model, but I can always go in later on if required. And other problem is the signed number problem, which is that solutions based on interpreting negative integers as a change. The signed number problem is basically the problem of problems with understanding negative numbers. even till till the 19th century, people had problems with negative numbers. Even people in higher mathematics had deep problems. They just could not handle the conceptions associated with it, and more so because in the West, for example, they didn't use the Indian notation, for example. They preferred to use Roman symbols, and so that definitely complicated matters for them as far as understanding of negative numbers is concerned. And while negative numbers are very common, for example, in Chinese mathematics, even in ancient Chinese mathematics, they are used in different senses. While therefore, okay, I'll come to that. And solutions, then recent solutions are like this. So those are based on interpreting negative integers as a change, as a state, or as a directed relation between numbers and quantities, and ideas of displacement that relate to a directed relation between numbers and quantities. For example, when a lift moves from floor 0 to the basement, from the ground floor to the basement, then that corresponds to one conception of, that's one way of introducing negative numbers. And if you have multiple levels below the floor, then one can really do the argument, but there are problems with that too. And in my 2021 paper, I argue that the problems of science is due to inconsistencies in the ascription of ontologies to the real numbers in concrete situations. And that is reflected in other examples that are provided in the literature. If the content of person connected with, okay. So there is a question which can be solved using that again. And there is also a graphical interpretation proposed by many, and that requires many additional assumptions generally. So that has that's more difficult to teach. Okay. And the methodological explanation can be couched in terms of existential import of signs alone. -5 is the same as non-existence of a 5 and can be read as this. And the relevant sign rules follow directly as follows, which is next thing, okay. So this is the non-existence of A and is therefore A. So these arguments are okay, that's what he saw. And for any A, B and Z plus, okay, this can be read as that. And that is already defined above. And this A times the non-existence of B is the non-existence of A times B. So these interpretations are compatible. And this is what I show there. Oh, these are some of the references, but how much time do you have? Okay. References. This is for a different reason. This is the handbook of methodology. Then these are examples where mathematical errors are studied. And here there is a pragmatic methodology. It's not really applicable to the school learning context. It's more intended for AI use in a certain way. And this is an overview paper which is quite useful. And this is a nice brief on student-centered learning, which this paper I mentioned. Then, yeah, these things are for the last part actually. Yeah, this is the paper on meteorological emptiness. This was also done in other places. And meteorology for STEAM and education research is an episteme paper. Then, yeah, there are more papers by me. And this is, this paper I am not discussing here. Huh? Yeah, this is an interesting paper. It deals with ethno-mathematics of cooking and how I use approximate reasoning there. For example, people have muscle memory. For example, they add almost certain amounts of material using their hands instead of actually measuring them. Now, that is due to muscle memory. And there have been many studies on this from different perspectives. People represent this using tensors and all. That is one way of doing it, but it's not really efficient, and a meteorological perspective is proposed here. So, huh? Huh?
Has there been any feminist study on this?
On this, yeah, there are papers which refer to it, but they don't go into all the details. That is what my opinion is. But this really goes into many of the details. This is a journal paper. Then, yeah, and this talk is based on this paper. It's Meteorological Methods for Education. It's my ICME paper, which was earlier this year. Okay, then, and the way I do the companion model is, the companion models which I spoke of earlier are much more complicated. They look somewhat like this. And this explaining it will take too much time, so I'm not going into that. But they look pretty complicated. This is how it starts. So there is a rough convenience lattice in which I add lot more additional structure basically. This is the companion model, and this combined with that gives a better understanding. And yeah, but to explain this I'll have to go back again. Yeah, for example, this is a problem. Okay, so the problem is simply solved. 2x plus 3 is 4x plus 1. And we study how to formalize different solutions provided by students. So students can give different kinds of solutions. They may be wrong, and it's typically necessary to refine solutions. Suppose you look at a worksheet, it won't really look very structured. So generally we'll need to do some restructuring at least. And here one of the assumptions is that teachers tend to upper or lower approximate the set of rules, concepts used in proofs based on their own understanding. Often they are too coarse. This is an observation which is obviously well justified. Okay, so these are part of that. So this is how I deal with it. I actually propose ideas of approximating solutions. And this means solution 1, not, yeah. I'll consider some solutions. This is an example of a solution. So various steps are mentioned, and start ones are wrong always. They are errors. And how does one formalize these? This is one of the questions which I do.
I have seen this page somewhere,
Hmm.
and I was actually
Hmm.
wondering what you wanted to say.
Hmm.
Is it, are these 6 steps, I mean, is it a sample, sample of a solution?
Yeah, sample
from
of a solution.
Solution.
Yeah,
One student.
one student. Some, yeah, some one or some students.
It's an actual case.
These are abstracted from actual worksheets.
No, it is not an actual case then, right?
It is, you can treat it as actual case for practical.
No,
part.
in that case there will be some dates and data from where, which
Yeah.
person, etc.
Yeah.
Or which from
Which
from
school?
which book, which
Which
this is necessary, but that's not given.
Yeah, it is not stated here because there I added some are not from real work, some are abstract. So that's why.
Here you see, I know at least Ramakrishna is here who works in this particular area,
Yeah.
and so maybe if he comments,
Okay.
because whether he is also facing this kind of mistakes.
No, students do make mistakes, and we are dealing with the formalization aspect. How do we formalize?
No, but this is not the formalization.
This
This is
not the
actually an
this is the actual
case.
solution.
Actual solution.
Yeah.
Formalization we have done in
Over
this
this.
algebra
Yeah.
part.
So, how do we deal with this? Yeah, so, and here we speak of approximating entire solutions. How does one construct them? That is the question. Suppose solution 1 is this, and there is a.
My point is that if it is not a real problem, then it will be a kind of exercise done without reason.
No, there are examples available definitely. There are no problems with that. We have plenty of books which have plenty of examples, so that part is not a problem. But these are abstract. Some are abstract, some are not abstract. Okay. So, and the main thing is that I propose, I speak of approximations of solutions, and basically what the approximation operator does is it annihilates negative or insufficient or defective understanding of specific operations or rules, and is therefore a special kind of approximation. So we need this kind of approximations to handle that. And so basically it's a long discussion on how to approximate, and then I get to the models, then I propose related models. So that's the idea, and if you want the details you can look at the papers and questions.
Unclear is that as a philosophical approach of I understand the mereological attempt, but when it comes to education, why do we want to formalize what is going on in the classroom? And do we see it as phenomena that is occurring, therefore I want to formalize?
Yeah.
Or, education is also a field of action, right?
Yeah.
You don't just see classrooms as phenomena, right? You want to intervene, you want to do things in a particular way.
When we want to construct...
So you want certain principles. No, I'm just saying that.
Yeah.
So it's an action-oriented arena, right? So what is formalize? And so I'm not against formalization. We're sitting here after all, right? What I want to know is, in your view, what is the purpose of the formalization? Will it clarify what is happening in the classroom, or
yeah, it will it will tend to clarify and also provide suggestions for teachers and maybe students also.
See,
through software aids.
Well, this thing is that I find formalization and these things problematic, because at least the mathematics I know and the mathematical formalization tend to be universal, right? For instance, when I see those axioms, when I see these things, I don't see child-centeredness, right? I mean, in the sense that this is fundamental principle of school math education, right?
Depends on
because different children learn in different ways, different students approach and different mistakes come in different ways. The same 2x minus 1, the mistake he makes is very different from the mistake I make. So how would I particularize things?
Yeah,
right?
when we want to deal with student-centered learning, then the conceptions will be different for different students.
Correct.
And we need to be able to construct the conceptual patterns in them.
Correct. No, will formalization help in that or hinder that? That is my... See, my thing is...
Formalization
tends to hinder it, usually, in my opinion. Formalization tends to look at universal features.
But when we use approximate ideas, then it's easier to formalize. And
okay.
So we
then easier to particularize.
Yeah.
Okay.
So that is one of the advantages. And if you have good parthoods, it's always better.
So to continue what Dr. Ramakrishna was saying, the very question, what is primal, strikes me. Is it topology or is it mereology? Topological relations are more easier to understand. So maybe instead of parthood, mereological, formalizations that would involve topology would be more understandable to us.
Topology requires a lot more. One needs much more.
More structure, of course, but the relationship of parthood is primal or the relationship of connectedness is primal? That's the question.
Oh, this is, it depends on the formal system in which you consider.
Yeah.
So
just a thought,
is connected to requires at least some understand. It depends actually on the other axioms that one assumes.
Yeah, this is the final one is just a comment. It's not a question.
Yeah.
So,
for example, you can use overlap instead of parthood in many systems.
Yep, I agree with you. And just to add to your complete thing, in morning I showed you some video understanding. I use a theory of mereotopology. So my C is primal. From C I define P. And from P I define overlap and all my videos work like that, and I get back to the...
Yeah. That's a spatial topology.
Yeah, that's a spatial one. So mereotopology.
Yeah, and that's also heavily studied.
That works better in, I think, activities of daily living. That's what they said. So I'm just wondering, that's not...
Yeah, but there are other kinds of parthood predicates used in real life, especially functional ones.
Yes.
So... yeah.
Any more questions? Comments? Okay, so then let's thank the speaker. And that is it for today. So for tomorrow we start at 11 with a talk by Kamal, and then we will have Amit give us a second talk. No. Start at 11 tomorrow with talk by Kamal. That's it.